Okay, online students, can you hear me clearly? Online students, can you hear me clearly? Can someone please confirm? Can you hear me clearly? Okay, thank you. Uh, so today we have to start optics, right? Today we have to start optics, and just to inform about the classes, there are two classes going on for 26 batch. In both classes, we started optics recently. You have the Sunday class. You have the Sunday class where I teach in both Sinhala and English. That means mainly in Sinhala. There's around like 120 physical students there, and here it's around 35 physical class students. So this is an entirely English medium class. So if it is manageable, it's okay for the Sinhala medium students to stay here. But if you are a Sinhala medium student, I prefer you join in the Sunday class. There also I have started optics just 2 weeks before. Okay. Yeah, so I started optics 2 weeks before in the Sunday morning class. Here we are starting optics today, uh, and we have to do some practicals from waves and oscillations, if I'm right. We have to do some questions from waves and not questions, practicals from waves and oscillations. That would happen today, as I remember, 6:30 in the 6:30 8:30 time slot. So we were doing hydrostatics and hydrodynamics in the 6:30 8:30 time slot only for today. Usually the class is from 3 to 6:30. Usually the class is from 3 to 6:30. Today also I'm doing optics from 3 to 6:30. But we have some practicals to finish in waves and oscillations lesson. From that one, so only for today in the 6:30 8:30 time slot, I'll be doing the remaining practicals of waves and oscillations lesson. Okay, that is the plan for today. It's just different only for today. Okay, so starting with optics, hope everyone got the tunes right. And for online students, we have to provide tunes, right? Yeah. Okay, so the tunes will be available in the Zoom chat now, and I'll provide you a number for you to contact and get the tunes delivered. Okay, I'll provide you a number today. You can contact that number and ask them to add you to the group, and also you can get the tunes delivered from that number. Okay, so talking about optics or light, there's nothing new in this syllabus. Okay, I mean, yes, there's something new like the measuring instruments kind of stuff, instruments kind of stuff. That means telescope, microscope, these kind of things, they are new. But majority of optics lesson, okay, majority of optics lesson we have covered in your O-level syllabus, and also in your like waves and oscillation lesson. That means talking about like in waves and oscillation, but not knowing waves and oscillations is not an issue here. Okay, if you don't know waves and oscillations, it's not going to be an issue for optics. But like reflection, refraction, diffraction, all kind of stuff we did in waves and oscillations lesson, right? So same thing happens with optics, okay, nothing new. Same thing happens with optics. That means optics is also a wave, right? Optics is also a wave. So as a result, whatever happened to waves, okay, whatever happened to waves, reflection, refraction, diffraction, everything happened in waves will happen to optics, okay, will happen to optics. So there's nothing new in this lesson. It's just a combination of waves and oscillations lesson and the O-level content. That means you have drawn a lot of ray diagrams in O-levels, right? So everything is similar here, okay. So now like talking about optics, usually this light waves, what is light waves? I mean, we have different waves, different electromagnetic waves, right? Like radio waves, RF waves, then gamma rays, X-rays, different rays, right? Then what is the difference in light waves? It's just the type of waves which makes a sensation in your eye. That is the only type of wave that means it's the frequency range which our eye can decode. Clear? It's the frequency range that our eye can understand and decode. Clear? So that range is usually 380 nanometer to 380 nanometer to 380 nanometer to 780 nanometer. 380 nanometer to 780 nanometer. This is the frequency range we are talking about. Clear? 380 nanometer to 780 nanometer. And like there's, I mean, how we draw a optic ray is just like in O levels. A line with a direction like this. That's how we draw a optic ray. Clear? This is how we draw an optic ray. Clear? Then there are different types of optic rays, like these are parallel rays. These are parallel rays. These are parallel rays. And this we call diverging waves. These we call diverging waves. Diverging waves. They are spreading out from a point. Clear? These we call converging waves. These we called converging waves. Clear? These we call converging waves. So these are parallel waves. These are diverging waves. These are converging waves. Clear? These are converging waves. Then talking about the sources of light. Talking about the sources of light. So, I mean, we can call them primary sources and secondary sources. Okay? We can call them primary sources and secondary sources. That means like there are primary sources, which means actually secondary sources are not sources. Okay? This is a primary source. This light bulb is a primary source. It creates light using some kind of a reaction, maybe chemical, maybe different some kind of a reaction. Using some kind of a reaction, this bulb, sun, these kind of things, they create light. Clear? They create light. Clear? Them we call sources. Okay? And what about this, maybe this book? What about this book? This one? This is not a source. Why? This is not a source. Then how can I see this? This is not a source. Then how can I see this? It turns into a secondary source. That's why. Clear? This is not an actual source. It just turns into a secondary source. That means light rays reach here, reflects, then returns to my eye. Clear? Light rays reach here, reflects and returns to my eye. As a result, I can see this. Clear? As a result, I can spot this. Clear? So these are secondary sources. Secondary sources are not actual sources. Clear? Okay. So now the next step we are just learning the terms here. Okay, nothing new. We are just learning the terms here. Next we have to talk about the medium. There are some media that allows light to go freely. That means take a glass, through a glass light can freely move, right? Light can freely move. I can see whatever happens in the other side of a glass, right? That means light can freely move through a glass. This kind of material we call them transparent material. Transparent material. And some materials you can't see anything. Take this one, take a wall, take brick, anything like that, even paper. You can't see anything through paper, right? So they are opaque. Clear? They are opaque. That means they don't allow light through them. Clear? They don't allow light through them. Then next we have translucent. That means something like a polythene sheet. Through a polythene sheet, a certain amount of light can come. Clear? Through a polythene sheet, a certain amount of light can come, but you can't see everything clearly. Clear? But you can't see everything clearly, but a certain amount of light can travel. Clear? So we call that translucent. Clear? Okay. So that's how we divide mediums, different media into categories. Clear? So these are just the terms. Okay. Now what we have to start learning is the properties of light. So up to this point what we did was just learning the terms required. Now only we are starting the theory points. So the first thing is reflection. Reflection. They haven't asked us to teach reflection in this syllabus. The reason is everything related to reflection was done in O levels. Okay. Everything related to reflection is done in O levels, and again in A levels waves and oscillations lesson. Clear? Okay, so they haven't asked us to teach reflection here, but I'm doing reflection because I have to show you one or two questions that are difficult, that are a bit different than the questions you did in O levels. Okay, because in O levels we learned the theory points, we did simpler questions from reflection, but there are much harder questions that they can give from reflection. Okay, although the theory is same. Okay, although the theory content is similar, it's nothing new. All the theory content is similar like in O levels, but there are, we can, like in A levels, the difference is you can have a easy theory, but there may be a very different question from that area, right? So we have to be like ready for those type of questions. So I have to go through some reflection questions today. So talking about reflection, what is reflection? Reflection is light reach a certain barrier, reach a certain barrier, and it returns to the same medium. Clear? Light returns to a certain barrier, but through that barrier it returns to the same side. Clear? It returns to the same side. This is reflection. Clear? This is reflection. And what are the laws of reflection? What are the laws of reflection? This is a 2D procedure. This is a 2D procedure. That means this is a 2D process. 2D process means light go through, take this board as a plane. Take this board as a plane. Light move in this plane, and this perpendicular line is also in this plane. Then definitely the reflected light must be on this plane. That means it is a 2D process. If it happens in this plane, it returns in this plane. It's not going to go through one plane and move to another plane. It's not going to move to another dimension. Clear? It's going to be two-dimensional. Clear? This is a two-dimensional process. Clear? Then the next one, what is the next one? What is the next reflection law? The next reflection law is if this is theta, if this is theta, if this is theta, this must be theta, right? If this is theta, this must be theta. Clear? These are the reflection laws. Clear? So in waves and oscillations we didn't try to learn these, but if you have an object here, then if you have an object here, then if you have a mirror here, where can you find the image? Where can you find the image? Light rays go like this, then it returns like this. Clear? It moves like this and reflects back like this. Clear? Then again it can move like this, then it reflects like this. Clear? Then it reflects like this. Clear? It reflects like this. Then if this angle is theta, this angle must be theta. Clear? If this is theta, this must be theta. Clear? Clear? Now the thing is, if I place my eye here, my eye will receive this ray and this ray. Clear? My eye will receive this ray and this one. Clear? Now, my eye doesn't know this story. That means they went here, they started here, they went here, then they reflected back. This story, my eye doesn't know this story, okay? My eye doesn't know this story. So when my eye doesn't know this story, as a result, what happens is, my eye traces back and it thinks that the image is, I mean, it thinks that these light were started at this point. Clear? Clear? That means my eye gonna receive a lot of rays, and using those rays, my eye will create this image, right? My eye will create this image. Clear? So my eye doesn't know this reflection story. Clear? My eye doesn't know this reflection story. It only captures these rays. Clear? So when my eye, using my brain, when my eye recreate this image, that means when it complete this diagram, it understands that these rays meet at this point. So as a result, the image I see is formed here. Clear? The image I see is formed here. Clear? Clear? That's how an image is formed in a reflection scenario. Clear? That's how an image is formed in a reflection scenario. Clear? Clear, everyone? Okay. Now, now you should understand, if this is theta, this must be theta. If this is theta, this must be theta. If this is theta, this must be theta. Clear? If this is theta, this must be theta. If this is theta, this must be theta. Clear? Then, now as you see, these two triangles are similar, right? These two triangles are similar. Clear? So as a result, if this length is L, this length must be L. Clear? As a result, if this length is L, this image must be, this length for the to the image must be L. Clear? So the conclusion is, when you place an object at a certain point, when you place an object at a certain point, its image will be formed at a similar distance. Clear? Its image will be formed at a similar distance. Clear? Clear? So as a result, I mean, if you place something like this, this point will be formed at a similar distance. Then this point will be formed at a similar distance. So as a result, you will see something like this. Clear? As a result, you will see something like this. Clear? So the image is always inverted in a mirror as a result. Clear? In a mirror, image is always inverted. Clear? Clear? So this is the story about reflection. So only new thing is, I mean, there's nothing new, right? Everything you knew from all of us, right? This part that I explained, everything you knew from all of us, right? Clear? Clear? Okay. So the reflection laws, how the image is formed, all these stories you knew from all of us, right? That's why I said that they haven't asked us to teach reflection in the syllabus, okay? And that's why I have mentioned these things in the note. That's why in ambulance they print ambulance as an inverted image. Why? Then only when you see through a mirror of your vehicle, you can see the term ambulance properly, okay? These kind of things I have mentioned in the tude. So make sure you are reading the tude. Let's move to exercise 1. That's the only important part in reflection, because there's nothing new here. Let's move to exercise 1. Try question 3. It's an easy one. Then 1, Then 2, go to exercise 1. You have your tunes available in the your tunes are available in the Zoom chat, and I'll give you a number. You can contact my coordinators and get your tunes delivered from that number. Anyone who need tunes in the physical class? Anyone? So in optics, the question, it's all about drawing a perfect diagram, okay? So in every question, I mean not for very simple ones like the third question. For the other questions, just try to draw a perfect diagram, then you would get the answer properly. Tunes are available in the Zoom chat. Put a message on the Zoom chat if you can't find the tute. An object moves at a speed, sorry, the third one, an object is placed between two parallel plane mirrors facing each other 20 centimeter apart and 8 centimeter from the other mirrors. As calculate the distance from the objects to the first two images seen in each mirror. So it's like this, right? The question is not that clear. It's my bad. Anyways, we can still understand the question. There are two mirrors like this. There are two mirrors like this. 20 centimeter apart. 20 centimeter apart. There's an object at a distance of 8 centimeters. There's an object at a distance of 8 centimeters. Then the image, the first two images, distance to the first two images they are asking. Clear? So it's quite straightforward. If this is 8, first image will be formed here at a similar distance 8. Clear? Then if this is 8, this must be 12. Then the second image will be formed at a similar distance as 12. Clear? As 12. Clear? So first two images will be formed at these 2 points. Clear? If they ask third and fourth images, then what would happen? Third and fourth images means, again this image will be an object for this mirror. Clear? This image, it will be an object for this mirror. Clear? So as a result, this distance is 12 plus 8 plus 8, 28. There will be another image at a distance of 28. Clear? 28. Clear? And what about this guy? There's an object at a distance of 12 centimeters. Clear? This is an image formed in this mirror. Clear? But this one will be an object again for this mirror, right? So as a result, what is this distance? This is 32. Another image will be formed at a distance of 32 centimeters. Clear? 32 centimeters. Clear? Like that it will happen until infinity. Okay? Like that this will happen until infinity. There will be infinite number of images in this scenario, but actually you won't see infinite number of images. Why? At each reflection there is an energy loss. Clear? At each reflection there will be an energy loss. Clear? So due to the energy loss, after a certain point the images won't be that clear. Okay? And after a certain point you won't see anything. Clear? So theoretically there must be infinite number of images. Clear? Theoretically there must be infinite number of images, but actually you will never see infinite images due to the energy loss at each reflection. Clear? That means at each reflection there will be a certain energy loss like this. Clear? There will be a certain energy loss like this. Clear? Okay? Okay. Do something like this. No, but I'll show that. I mean, if someone asks, I mean the ray diagram of this guy. Okay, yeah. If someone asks me the ray diagram of this guy, how can I draw this? If someone asks me the ray diagram of this guy, how can I draw that? It's like this. Or else, if someone asks me the ray diagram of this guy, this one here, how can I draw that? I mean, how it works is like this. I mean, this is not connected with the question. Question is quite simple, but I needed to teach this part actually. you have a system like this. Now you have an object here, you have an object here, clear? So what happens is there will be a light, you have an object here, there will be a light emitting from this object like this, clear? Like this, and it will reflect back like this, clear? Then there will be another light going out like this, clear? And it will reflect back like this, clear? That's how this image is formed, okay? That's how this image is formed. That's how this first image is formed, clear? Clear? Now this ray, it will continue like this. This ray, okay, this one, clear? This ray, it will continue like this, it won't stop. It will continue like this, clear? And this ray, this one, it will also continue like this, clear? Clear? And they will be reflected at this point. They will be reflected at this point, clear? And this one will be reflected at this point, clear? And they together, that means I'm gonna draw a line from this one and I'm gonna draw a line from this one. They together will create an image here. See, they together will create an image here. That's how the third and fourth images are formed, clear? And this will happen until infinity, okay? This will happen until infinity. Now these rays will go and reflect here, will eventually create an image here. Like that, the reflection will continue until infinity, clear? Clear? The reflection will continue until infinity. So that's how the third object is formed, third image is formed. And you can see fourth image, fifth image, sixth image happening like this, clear? Clear? So it's good to have a very good common sense about these ray diagrams when you are doing optics, okay? It's really important to have a very good common sense about ray diagrams when you are doing optics, clear? How things happen. It's easy to know that how things are reflected. What is the if the object distance is 5 centimeters, image distance is 5 centimeters, and there will be secondary images, third, fourth, fifth, sixth images. But it's important to know how it actually happens through ray diagrams, okay? Clear? So it's, I mean, if you need, you can draw this. Then move to question number 1. Move to question number 1. Exercise 1, question number 1. I'll give enough time for these questions because these are quite important. We are not teaching, we are not going to teach reflection in this syllabus. So all we have to do is doing these questions and understand that there can be questions like this. After question number 1, move to question number 2. If you are done with question number 1, move to question number 2. So the reason I'm not teaching these questions directly, I'm asking you to try these questions first. There's nothing new, no new content. It's just applying the same theory to a different question, that's all. So in question number 1, all you have to do is draw a perfect diagram. Okay, draw a perfect diagram. That's how we do optics questions. That means best option is for me, an object moves at a speed of 5 meters per second towards the plane mirror. The mirror is moving at a speed of 1 meters per second away from the object, moves at a constant speed. Find the speed at which the image moves and state the direction of motion. An object moves at a speed of 5 meters per second towards the mirror. Mirror is moving at a speed of 1 meters per second away from the object. Clear? So they need us to find the velocity of the image. Clear? They need us to find the velocity of the image. So in a scenario like this, for me, the simplest solution is, okay, in a scenario like this, for me, the simplest solution is drawing the diagram 1 second before and 1 second after. Clear? Drawing the diagram 1 second before and 1 second after will give you the direct answer, right? Clear? So drawing a very nice perfect diagram at a 1 second interval. Clear? I think that's the best thing that you can do. Clear? So exercise 1, part 1. An object moves at a speed of 5 meters per second towards a plane mirror. There's a mirror. There's a mirror. There's an object. It moves at a speed of 5 meters per second. It moves at a speed of 5 meters per second. And there's a mirror. It moves with a velocity of 1 meters per second. So if the length now is L, if the length now is L, image is formed at a distance of L, right? If the distance to the object is L, distance to the image again would be L, right? Distance to the image would be L. Clear? Clear? Now, after 1 second, what's going to happen? Is this clear? Is this clear? Now, the object is at a distance of L and the image is at a distance of L. Clear? So, after 1 second, what's going to happen is this guy will move 5 meters, right? That's the meaning of 5 meters per second, right? Meaning of 5 meters per second is after 1 second, this object will move 5 meters, right? So it will move 5 meters. Clear? It will move 5 meters. Clear? And again, after 1 second, the mirror will move 1 meter, right? The mirror will move 1 meter. Is that clear? After 1 second, the object will move 5 meters. The mirror will move 1 meter. Clear? Clear? Now, what is the distance to the object? This is L minus 5. Then this. L minus 5 plus 1, right? This is L minus 5 plus 1. Clear? Which gives me L minus 4. Clear? L minus 4. So here the object is at a distance of L minus 4 from the mirror. Clear? Then the image is formed at a distance of L minus 4. Clear? Then the image is formed at a distance of L minus 4, definitely, right? Distance to the object equals to the distance to the image. Clear? If this is L minus 4, this must be L minus 4. Clear? Now you have the answer, right? Now you have the answer. Why? You know the position of the object 1 second before, and you know the position of the object 1 second after. Clear? So now you know the distance traveled by the image in 1 second. Is that clear? What is the distance traveled by the image in 1 second? This is L. This is L. Uh, this is L minus 4. Then I can write this length is L. If the distance traveled by the image is x, if the distance traveled by the image is x, I get L equals 1 plus L minus 4 plus x. Clear? This is L. Clear? This is L equals 1 plus L minus 4 plus x. Is that clear? L equals 1 plus L minus 4 plus x. Clear? Clear? So I get L to L cancels out. X equals 3. That means within a second, the image moves a distance of 3. That means the velocity of the image is 3 meters per second. Clear? 3 meters per second. Clear? Write this down. See? So all you need is a perfect diagram. And I mean, if anyone is struggling, especially even in mechanics, the main reason is, in this question also, it's not difficult, right? This is not a difficult or complex question. Only one theory point was used. Distance to the object equals to the distance to the image. What you are not doing is drawing a perfect diagram. That neatness is not there. So even for mechanics, what you need is that neatness, okay? You are not, the thought process is not well organized. That is the main issue that I see when students are struggling in mechanics. Thought process is not well organized. So here, the diagram is well organized. What happened was well organized. What happens 1 second before, 1 second after. So even in mechanics, if someone's struggling in mechanics, the main reason behind that is your thought process is not well organized. For me, if I get a mechanics question, I read it properly. I read it twice. I understand it very well. And I take a lot of time and try to include the data set in a perfect diagram. I try to include the data set in a very perfect diagram. Clear? Then I analyze that perfect diagram. I first think what are the equations that I can use here. If it is not clear, assume that it is a motion equation question. If it is not clear, I'll write the equations aside. Now I can see the equation. Now I can see the data set. Now I can see using this data, which equation can I use? Which equation can I use? Like that, the thought process is well organized. You can do any maths question and mechanics question, especially in physics. When the thought process is well organized, same goes with optics and all. Okay? So we need a perfect diagram, perfect thought process. Clear? Otherwise what you are doing is you just draw a random diagram from the given data and you try this, try that. You actually don't complete one method and go to the next method. You go through one method, okay, on the way you give that up and go for another method. It's not well organized. Clear? So for you, if you need to get good especially in mechanics, what you need to do is draw a perfect diagram and have a well organized thinking pattern. Clear? Go to question number 2. Question number 2. Okay, question number 2. Question number 2. It's okay. I mean, if you can't get the answers for this, okay, because all you have is the knowledge from O levels about in this area. All you have is the knowledge from O levels. So you haven't seen these type of questions in O levels. That's the main reason that I'm doing these questions before moving to the main part in our syllabus, okay? Because although this is not, they haven't asked us to do a lot of questions from optics in this syllabus, still they can give questions up to this extent, right? Because it's nothing new. It's the same concept but a difficult question, right? It's the same concept you learned in O levels but a difficult question using the same concept. So in the question number 2, a child 160 centimeter tall stands in front of a plane mirror. His eyes are located 10 centimeter from the head. Below, calculate the minimum height the plane mirror must be for child to see his full reflection. That means there's a child like this. The height of the person is 160 centimeters. Height of the person is 160 centimeters. Eyes are located 10 centimeter from the head. Eyes are located 10 centimeter from the head. What is the minimum height of the plane mirror must be for the child to see his full reflection? Okay. So there's only one simple requirement for this. What is that? For this person to see his full body, whatever the light rays moving away from the head should return to the eye. Clear? Whatever the ray, and let's assume that your mirror is here. Whatever the ray moving away from your toe must return to the eye, right? This is the basic requirement. Clear? Now if you have a mirror like this, it's enough. Clear? If you have a mirror like this, it's enough, right? Clear? Whatever the ray coming out, whatever the ray represents the head should return to the eye. Then you can see the head. Clear? Whatever the ray belongs to this point should return to the eye. Then you can see this point. That means in between you can see everything. Clear? Clear? So this is the minimum length and it should be 80 centimeters, right? It must be 80 centimeters. Why? It's the half of the total height. Why? See, these are reflections. In reflections, everything is symmetric. Okay? In reflections, everything is symmetric. So, if this is 10, definitely, since this is a symmetric diagram, this is 5 and this is 5 because this is a symmetric diagram. So, this part is 5 then. This part is 5. Clear? Then again this is symmetric. So, if this is 10, this is 150. Then this is symmetric. So, as a result, this is 75. This is 75. Clear? This is 75 and this is 75. Clear? Clear? Then, if this is 75, this is 75. So, as a result, this is 80. So, you don't have to go through this whole process. It's actually half of the person's height. Clear? I mean the location of the eye, nothing matters. Clear? Nothing matters. The height of the mirror must be half the height of the person. Clear? Clear? And you may ask this question, but you have seen some mirrors, very small mirrors, still you can see everything, right? Very small mirrors, you can see everything. For an example, side mirror of your vehicle. Side mirror of your vehicle, you can see it's a very small mirror. But you can see yourself, right? Clear? Side mirror of the vehicle. There's a lot of mirrors like that. Even some mirrors at hotels like that. You can see, right? Although the mirror is very small, you can see. Then how does that happen? A lot of mirrors are not plane mirrors. They are convex mirrors. Convex mirrors, a very small mirror can show a huge area. Clear? So it's a different story. Clear? A lot of mirrors, even some mirrors, even some mirrors that you think that it is a plane mirror have a very small curvature. A very small curvature. Clear? So although we see them as plane mirrors, they are not plane mirrors. They are convex mirrors. For convex mirrors, the story is different. Clear? Even a very small convex mirror can show a huge area. Clear? But that's not how plane mirrors work. Plane mirrors work like this. Clear? So definitely you need a minimum of 80 centimeters as the height of the mirror to see the full image. Clear? Clear? This is the answer for question 2. So my main requirement was to show you that there can be questions like this. Okay? Nothing else. You just have to know that there can be questions like this. Okay? That means much difficult questions from the same simple theory points you know in optics. Clear? Write this down properly. Properly understand and draw. Okay? Okay. So next. Refraction. Next property. Nothing new again. Okay. Refraction. You already know refraction laws and all. Okay. You again know refraction laws and all. So what is refraction? What is refraction? Attention. A light ray reach a certain boundary, clear, but it doesn't reflect, it return or it jumps to the next medium. Clear? That means refraction is a light ray reaching a certain boundary, but it moves to the next medium. Clear? That's refraction. Clear? Then again, you know, if this is I, if this is R, as I remember in O levels you learned the Snell law like this. If the velocity in this medium is v1, if the velocity in this medium is v2, as I remember in O levels you learn Snell law like this, sine I over sine R. Clear? That's how you learn Snell law in O levels, as I remember. Clear? This is not a very accurate thing. The reason is in O levels they don't define this refractive index. Can you remember the term? Refractive index. In O levels they don't properly explain this refractive index. So this is not that accurate. Clear? This is not that accurate. Then in waves and oscillations lesson, we learn the Snell law like this. Can you remember? As I remember, V1 over V2. Sin I over sin R equals, as I remember, sin I over sin R equals V1 over V2, right? We learn something like this. Can you remember? In waves and oscillation lesson, that's how we learn the Snell law, right? Sin I over sin R equals V1 over V2. This is the most general form of Snell law. This is the most general form of Snell law. Okay? And I mean, I don't have to mention what is Snell law, right? Now you already know. When we talk about refraction, there are two properties, two laws, right? Two laws of refraction. What are the two laws of refraction? One thing is, again, it's also 2D. It's also 2D. That means if this ray is in this plane, if this perpendicular line is in this plane, then the refracted line is also in this plane. Clear? Clear? That means it's a 2D process. It's not going to reach a third dimension. Clear? Clear? Then at the same time, the next thing is like this, the next law is Snell law. In all of us we learn the Snell law like this, n equals sin I over sin R. In waves and oscillation lesson we learn Snell law like this, sin I over sin R equals v1 over v2. Yes, this is the most general form of Snell law. Why? The reason is this refractive index is usually defined in optics. In waves and oscillation lesson we worked with sound waves, optic waves, RF radio waves. In waves and oscillation is a general lesson. So in that one we can't always find the refractive index. Refractive index is usually defined for waves, defined for optic rays. So we can't always find a refractive index for a medium. Clear? So that's why we learned the most general form of Snell law, which is this, in waves and oscillation lesson. But since this is the optics lesson, okay, since this is the optics lesson, it's good to know the Snell law which uses the refractive index, not the velocities. Clear? It's good to know the Snell law which uses the refractive indices. Clear? So before that, first we have to learn the definition of refractive index. What is the definition of refractive index? Definition of refractive index is, in a vacuum, optic rays can move at this velocity c. C means 3 into 10 to the power 8, right? C means 3 into 10 to the power 8. Clear? In a vacuum they can move in this velocity. Clear? So if the refractive index is n of something, n1, let's take n1. This is the refractive index of first medium. It is C over V1. Clear? C over V1. Clear? That means the refractive index of a certain medium means velocity of light in that medium, and here velocity of light in a vacuum. Clear? Then N2 is C over V2. Clear? N2 is C over V2. Clear? Now, the actual Snell law is like this. Okay? The actual Snell law is like this. Actual Snell law is sine I over sine R, sine I over sine R equals refractive index of second medium relative to the refractive index of first medium. Clear? Refractive index of second medium relative to the refractive index of first medium. Clear? So the actual Snell law is this. Clear? So the actual Snell law is this. In our O levels we didn't define this very well, but in A levels we define this very well. Actual Snell law is sine I over sine R, sine I over sine R equals the refractive index of second medium relative to the refractive index of first medium. Clear? So this is the proper Snell law. Clear? This is the proper Snell law. Okay? So this gives me refractive index of second medium is N2. Refractive index of first medium is N1. So this is the refractive index of second medium relative to the refractive index of first medium. Clear? Then N2 I can write as C over V2. C over V2. N1 I can write as C over V1. Clear? C over V1. Clear? Then C to C cancels out. C to C cancels out. Then I get V1 over V2. Clear? V1 over V2. Clear? So actually it's the same law. See? It's the same law actually. Clear? It's the same law. It's the same law but represented using the refractive indices. Clear? Is that clear? Is that clear? So this is the proper Snell law. Is that clear? So I mean you have to know all these things. So write this row in your book. It's there in your book, but it's good to write. So write this row in your book. So and how I usually write the Snell law is like this. It's easy to remember like this: N1 sin I, N2 sin R. So I usually cross multiply. I cross multiply N1 here and I cross multiply sin R here. So I usually write as N1 sin I equals N2 sin R. Okay? That's how I usually write this. Okay? I usually write this as N1 sin I equals N2 sin R. Clear? That's how I usually write the Snell law. Clear? That's how I usually write the Snell law. Clear? Is that clear, everyone? Clear? So try exercise 2. Try exercise 2. Question number 2A. Question number 2A. And F. And question number 3 in exercise 2. Try these questions. apply the Snell law. It's just n1 sin I equals n2 sin R. That means refractive index of this medium into sine this angle equals refractive index of this medium equals sine this angle. Clear? Okay. So apply the law and try to get the answers. So if there are some difficult, I mean, if you don't have a logbook, you don't have to solve for the final answer. Just write the proper equation and move to the next question. So the first one, exercise 2, question 2a, quite straightforward. Here it's here it's 30. Here it's 30. Here it's 25. Here it's 25. This is air. So usually you can take the refractive index of air as 1, okay? Usually you can take the refractive index of air as 1. Usually the refractive index of a vacuum is 1, okay? Usually the refractive index of a vacuum is 1. That means why in a vacuum the refractive index would be C over C, which gives you 1. But in air we usually consider it as very similar to a vacuum, okay? Air we usually consider it as very similar to a vacuum. Clear? So as a result, we take the refractive index of air as 1. Clear? So I can apply the Snell law here. I need to find the refractive index of this medium. So the equation is n1 sin I equals n2 sin r. So n1 is 1, sin I is sin 30, this is n2, which is n, this is sin 25, clear? 1 sin 30 equals n sin 25. So I get n equals sin 30 over sin 25. Clear? N equals sin 30 over sin 25, and you can use the logbook and calculate the answer. Clear? So in question F, they need us to find, I think, this the remaining angle, right? That means they need us to find this angle in question number F. In question F, is this clear? In question F, they need us to find, this is the diagram. Here you have air, that means the refractive index 1. Here you have water, that means the refractive index is 4 over 3. Here the angle is 80. Then this medium, the refractive index is 1.5. So here the question is not that clear. I think they need us to find this C. And also they need us to find this angle. Let's call it theta. They need us to find this angle theta. That means the refracted angle at this point. Clear? They need us to find C and theta. Clear? Clear? So we can apply Snell law to this point and this point. Clear? So we can apply Snell law to this side and this side. This is 1 sin 80. This is 1 sin 80. 1 sin 80 equals 1.5. I'll take this angle as alpha. 1.5 sin alpha. 1.5 sin alpha. Clear? That's how you apply the Snell law. Refractive index of this medium into sine of this angle. Refractive index of this medium into sine of this angle. Clear? So you can find sine alpha like that. So I get sine alpha equals sine 80 over 1.5. Sine 80 over 1.5. Clear? So definitely bring a logbook. We can't continue this question without a logbook after this point, right? Because we have to find alpha somehow. How to use the calculator. Only calculator. So definitely bring a logbook, okay? We can't continue optics without a logbook. Thank you. So we get here sine 80 over 1.5. which gives you 0.66, and then alpha is uh, sine inverse 0.66, which gives you alpha equals 41.3 roughly. So you don't usually use a point decrease, so 41 18. That's the answer you're going to get from the logbook, which won't be the same answer, something close to this. So now we know alpha. If alpha is this, C is this, right? Why? Alpha and C is equal, right? See? Alpha and C is equal, right? Clear? So the angle C would be the same one, 41.18. Then if this is C, what is this? If this is C, what is this? I'll take it as I'll consider it as maybe I. I'll call this angle I. Clear? I'll call this angle I. So I can get I equals 90 minus C, right? 90 minus C. Clear? Which gives me 90 minus 41.18. Clear? Clear? So this will give me 42 and 48. Is this right? Yeah. Why do I need angle I? When I'm applying Snell law to this point, I must use I, okay? I can't use C. Clear? Because when you're applying the Snell law, what you need is the angle between the perpendicular line and the ray, okay? When you're applying Snell law, what you need is the angle between the perpendicular line and this ray. Clear? So you have to find this angle. Clear? So that's why I need to find I. Now I can apply Snell law again to this point, here and here. I can again apply the Snell law to this point and this point, which gives what is this medium? 1.5. 1.5 sine I. 1.5 sine I. Sine I means this one. 48, 42 equals 4 over 3 sine theta. Equals 4 over 3 sine theta. Now using this you can find sine theta. Clear? Using this you can find sine theta. Clear? That's how we continue this question. Move to question number 3. Try question number 3 quickly. Question with a sphere. Try question number 3 quickly. Put a message if you can't find the tute. Put a message in the Zoom chat if you can't find the tute. So when will the term tests will be over? Are you done with term tests? You have term tests these days, right? Yes, right? What about this side? Anyone having term tests these days? No? No. In the future, within 1 or 2 weeks? Yes. When? Not next week, week after that. What about this side? Because I mean, I had to start heat parallelly. Okay. I mentioned that I had to start heat parallelly. We are going to do heat parallelly with optics for this class so that we can finish things quickly. I mean, you don't have much time, right? Only 1 year left to A levels, okay? So I mean, we are at a good stage, okay? We have done up to optics. It's good. But I think it's not enough. That's why I'm starting 2 lessons parallelly, and heat is a very like hectic lesson, long and a lot of content, so it's good to finish that early. So we have to start heat parallelly with optics. That's why I'm waiting until your term tests are over, because I mean, if I start something with term tests, you're not going to do it properly, right? So that's why I'm waiting a bit until your term tests are over. But it looks like we can't stay, like some people have term tests even after 2-3 weeks. So anyways, let's start within 1 or 2 weeks. Soon after we are done with hydrostatics and dynamics questions in 6:30, 8:30 session, let's start doing optics. Sorry, let's start doing heat. Okay, question 3 states, find the angle of emergence and the total deviation of the ray AB when light ray AB passes through the glass sphere and exits into the air. Okay. This is a glass sphere. Attention. This is a glass sphere. And there's a light ray reaching like this. What is this angle? This is 30. Then it goes like this. Then definitely this angle must be 30, right? Definitely this angle must be 30, right? Clear? I can call it R. I can call this R and try to find this. Anyways, you are going to get 30, right? Why? Why? If this is 30 and if this is I can apply Snell law here and here. Then if this is I, definitely this is I, right? Definitely this is I. Why? This side and this side is equal, right? This side and this side is equal. So if this is I, this must be, if this is I, this must be I, right? So if this is 30 and this is I, then if this is I, this must be 30, right? That's how the Snell law works. Clear? That's how the Snell law works, right? Clear? Why? This is air and this is glass. So I can write 1 sine 30, 1 sine 30 equals 1.5 sine I. 1.5 sine I. Then again here and here I can write 1.5 sin I equals again 1 sin R. 1 sin R. This is the Snell law. Clear? This is the Snell law. So 1 sin 30 equals 1 sin R, which makes R equals 30, right? Clear? 1 sin 30 equals 1 sin R. That means 30 equals R. Clear? 30 equals R. Clear? You can get the answer directly like this in this question. Clear? Write this down. So you don't have to write anything up to this point, but after this point you have to write notes, because I had to remove everything from this note to make sure that you are remembering things, because in optics we may have to make sure that we are drawing these diagrams few times, especially in the class once and twice maybe at home, and make sure that the diagrams are in your muscle memory. You can quickly draw the diagram, because in optics they expect that. Write this down. So a reminder, today's plan is also I'm gonna do optics until 6:15, around 6:15, 6:20. Then around 6:30, 6:40, I'm gonna start waves and oscillations practicals, 6:30 to 8:30. There are a few practicals remaining, 2-3 practicals remaining for us to do in um, waves and oscillations lesson, right? So we'll finish those questions in 6:30, 8:30 time slot. Uh, I'll repeat this again. So this is the perpendicular line. Usually perpendicular line drawn to a circle is its radius, right? Clear? So again this is the perpendicular line at this point. Again it should be radius. Clear? So if this is 30 and this is I, consider this triangle. Consider this triangle. This is R radius and this is R. Clear? Then if this is I, this must be I. Clear? If this is I, this must be I. Then again I and R. Clear? Got the idea? Clear? Nice. Okay. Again, next part. And there's something like this again. Like partial reflection, partial refraction is always there. Okay. We learned it in waves and oscillations also. There's nothing like perfect reflection, perfect refraction. It's not going to happen. That means here what we are talking about is it's just energy, right? It's just energy. That means light is an energy, right? Light is an energy. So what happens is, when a certain energy reach here at this point, a certain amount of its energy will reflect like this. That means a certain amount of its energy will fall to the same side, and certain amount of its energy will fall to this side. Clear? So there's no perfect reflection or perfect refraction. What happens is, when a certain amount of energy reach this point, a certain amount of energy will fall towards this side and a certain amount of energy would fall towards this side. Clear? Clear? So there are certain types of materials which supports refraction. In a situation like that, there's a partial reflection. Partial reflection. Partial reflection means a very small amount of energy will be reflected. Clear? And there are some materials like a mirror which supports reflection. In a scenario like that, there's partial refraction. That means a very small amount of energy will be refracted. That we consider as the energy loss. Clear? For an example, when you are looking at a glass, you can perfectly see everything in the other side. But at the same time, you can slightly see your own reflection, right? Take a glass. In a glass, you can see what is on this side. Clear? Clear? That means it supports refraction very well. Clear? It allows light to pass through it. Clear? But at the same time, you can see your own reflection, right? That means a certain amount of energy will fall to this side and certain amount will reflect back. From these reflected rays, you can see your own image. It's a very weak image, right? Why? A lot of energy will be refracted towards this side and a very small amount will be reflected. Clear? From that very small amount of energy, you can see yourself. Clear? And I mean, this is an area like we are like working a lot. That means when it comes to optics kind of stuff, that means energy kind of stuff. Okay? When it comes to energy kind of stuff, I mean, there are 2 or 3 main areas we invest in science usually. About the larger things, that means what happens at far away in the universe. And so we spend a lot for that. We spend a lot for that to analyze what happens in the universe, how things started and all. Clear? That's why we spend so much, like Hubble, James Webb, Space Station, International Space Station. Now it's out of duty, right? Now we have to send a rocket to push it away from our orbit. Now the plans are going on. I think within 2-3 days it will be pushed away from our orbit. Otherwise, at a certain point, it would fall back to Earth. So to avoid that, we have to push it away from our orbit, so that it can go wherever it need. So so we usually spend a lot of money on this part. What happens far away? What happens far away? And again, what happens at a very small scale? That means particle physics. You have another lesson, particle physics. That means what happens at a very small scale. That means you can keep dividing things. You can keep dividing things until they are very small. That means initially we thought that wood is wood, plastic is plastic, metal is metal. It's one single thing. But later we analyze, you can break it into parts, and there are things like atoms, things like neutrons, protons, electrons. Then we thought that it's over. We have electrons, protons, neutrons, and that's over. No, it didn't stop there. Then we identified that you can break neutrons and protons into smaller parts, which we call hadrons, and like not actually hadrons. It's not hadrons. I can't remember the name. You can break neutrons and protons into smaller parts. You have another lesson teaching this area. Yeah, quarks. Nice. Quarks. We can break neutrons and protons into smaller parts called quarks. Clear? Then like that, we have to break it into very small parts. So we invest a lot in that area. We have particle accelerators for this. Particle accelerators cost a lot. That means you can see this happening when particles move at a very high speed and collide with each other. For this, you have to accelerate these particles to a very high speed. What is the highest speed that we have ever seen? 3 into 10 to the power 8. 3 into 10 to the power 8. So usually in a particle accelerator, we accelerate protons and neutrons to speeds like 2.99999 into 10 to the power 8. Very close speeds. Okay, very high speeds we accelerate. So for this, we have a 30 kilometer particle accelerator. That means we take a particle and we accelerate it for 30 kilometers. We accelerate it for 30 kilometers. That means they have cities. Under the whole city, you have a particle accelerator. Okay, under the whole city, you have a particle accelerator, 30 kilometer particle accelerator. We will be accelerating these particles for 30 kilometers and let them collide with different materials. Then they will break into very small parts. Then we can analyze them. And I think now it's over. We are building a 100 kilometer particle accelerator too. There's a 100 kilometer particle accelerator too. So we are searching in that area. And the next area that we invest a lot in science is energy. Energy. Why? Energy, initially we thought energy can't be moved into parts. That means energy is one single thing, like water. Okay, energy can flow. You can't break energy into parts. But recently we identified, not that recently, energy also quantized. That means energy consists of small particles of energy. That means this light ray, it is not one single bunch of energy, no. It is, we can break it into very small parts. We can break it into very small parts called photons. Photons. Okay. That's what we call the quantum physics. That's how the quantum physics started. Okay. By breaking energy into small parts. Using quantum physics now we are doing a lot, right? Quantum computers kind of stuff. I mean, even in our computers, what is the main limitations? Electricity carries data, right? In our computer, we need electricity. Why? In our computer, electricity carries data. As a result, our computers are really slow. Although we think that it's fast, yes, it can do billions of calculations per second, yes. But still it is very slow. Why? Electricity carries energy. But again, if we can carry energy at this speed, if we can carry information at this speed, we can do a lot. So that's why we have quantum computers. Now it has been the main security threat, right? Why? Your Facebook passwords and all works due to this security. Why? They ask you to put letters, put symbols, put capital letters, put simple letters. Using this, there's a lot of permutations, right? That means you have millions of permutations when you type a password like that. That means it can be lot of possibilities, right? Capital A, capital B, different names. It can be billions or trillions of possibilities, right? But the problem is a quantum computer is so fast that it can try all these permutations within like 5 minutes. So until now, any system can't be hacked by trying the password again and again. It would take years for any computer. But for a quantum computer, it carries signals using photons. So it carries information at this speed. So within like 4 or 5 minutes, it can try all the permutations available. So with commercialized quantum computers, nothing safe. Now they are commercializing the quantum computers actually. Will be market, I think. Will be in the market soon, but not very recently. So that's the next main area we are focusing on. So I just mentioned like, so here even though we are discussing about the reflection laws and all, now this concepts does not exist actually. Now we break it into parts and analyze a photon, which means we quantized energy. We have broken energy into smaller parts, and now we analyze what happens to these energy particles. When we analyze energy particles, these things are very nice. Now we can see when an energy particle reach here, what happened to this particle? What happened to this particle based on the angle, based on the vibration of that particle, based on different scenarios. This particle can fall into this side or this side. Clear? For an example, assume that you have an energy particle, and definitely this is a glass. In a glass you have gaps. Okay? When if you use a very good microscope, you can see gaps in anything, right? So there are gaps in a glass. And you have an energy particle vibrating like this. And if the vibration of this energy particle is very small, it can go through this. But if the vibration of this energy particle is very high, It can't go through this, it would fall into this side. So I mean, this is not actually true. Okay, this is just a demonstration about how this is actually analyzed. Okay, this is just a demonstration of how these things are actually analyzed. Okay, it's not like that. It's not like energy falls and certain amount of energy will be reflected, certain amount will be refracted. It's not random like that. Based on a energy particle by particle, we can analyze this. Okay, you take one energy particle, that energy particle has a certain velocity, has a certain vibration, has a certain wavelength, has a certain frequency. Based on the properties of this particle, we can decide whether it's going to reflect or refract. What is actually happening is not reflecting or refracting. What is actually happening is these energy particles are moving through the gaps, clear? Okay, but gaps in the sense it's not physical gaps actually. Sometimes it's not physical gaps. Okay, there are different scenarios, but what actually happens is it's just water going through a net. Okay, certain amount of water will go through the net, so certain amount of water will hit the net and return to the same site. That's what we call partial reflection and partial refraction. Okay, so it's a huge area of science, but we just analyze it as, I mean, in a very simple way. Okay, but it's not that simple, clear? It's not that simple. Okay, so we are done with refraction. I had to do more questions, but I prefer if you can try questions at home, then I can do the questions here. Okay, because applying this Snell law is not rocket science. Okay, I mean, so whatever the question you have, all you have to do is applying the Snell law. Okay, so the whole exercise 2 is applying the Snell law again and again. Okay, so you can try that home. But talking about the refractive indices, attention, talking about the refractive indices, n, I said that n1 equals C over V1, n2 equals C over V2. And what is the meaning of this one? What is the meaning of this one? 1 and 2, it's the refractive index of n2 over n1, right? It's the refractive index of n2 over relative to n1, clear? You can write this if you like this, 1 n 1 over n2, right? If you like, you can write it this way, right? 1 over n1 over n2, clear? And you can write this as 1 over n. This is refractive index of 1 relative to refractive index of 2, right? So you can write 1 n2 equals 2 n1. These things are simple, right? Clear? So I mean, the reason for me to mention these things is sometimes you don't get the refractive index. Sometimes you have the wrong refractive index. That means you need 1 and 2, you have 2 and 1. In a situation like this, just use this. Okay, clear? And again, if you have 1 and 2 and 2 and 1, if you multiply these 2 and 3, if you multiply these two, what would you get? 1 and 2 into 2 and 3. Just mentioning, you can understand this by yourself. 1 and 2 into 2 and 3. 1 and 2 means n2 over n1. 2 and 3 means n3 over n2. So n2 to n2 will be cancelled out. Then you get n3 over n1, which gives you 1 and 3, clear? Which gives you 1 and 3, clear? So it's simple like that. Okay, 1 and 2 into 2 and 1 equals 1 and 3, clear? So sometimes you may see that you don't have enough data, but you have enough data. You just have to analyze the refractive indices, compare them, multiply them, divide them, and create the required refractive index. Okay, in certain scenarios they won't directly give you the required refractive index. Okay, they won't directly give you the required refractive index. Sometimes you will have to multiply or divide refractive indices and get the required refractive index. Clear? Okay, it's the time for interval, right? Or shall we continue until 5:30? No, we are going to finish at 6:15, right? Yeah. So next we have to do is real depth and apparent depth. You have learned the same thing in O levels, right? Real depth and apparent depth. That means if you have water here, if you have a coin here, you won't see this coin here. You would see the coin here, right? This is the real depth, this is the apparent depth. So how that happens, the equations related to that we have to learn. Okay. So I'll give you the interval. I'll start at 520, around 520. Uh, and after the interval, you can try some questions from exercise 2 also. Maybe question number 4. Exercise 2. Question number 4. Okay, so the next concept, real depth and apparent depth concept. Real depth and apparent depth concept. That means like if you have something here, if you have a certain object here, and maybe assume that this is water, assume that this is water. So the light rays will go like this, right? Light rays will go like this. Clear? Light rays will go like this. Clear? This will not refract, right? This will not refract. Why? It's 0 degrees, right? It's 0 degrees. So 0 degree rays will go straight, right? Clear? Then what will happen to this guy? What will happen to this ray? It will refract like this, right? It will refract like this. Okay. So now again, I have my eye here. I have my eye here. Clear? So my eye will receive these two rays. Clear? My eye will receive these two rays. Then again, my eye don't have a separate brain. Okay? As a result, it would try to locate, it would try to recreate the image, right? It will try to create the image. I mean, your eye doesn't receive the object, right? What it receives is a set of rays from the object, right? What your eye receives is a set of rays from the object, right? So all your eye can do is recreate what it see, recreate the image using the rays it captures, right? Clear? Your eye don't get to see the object. What it sees is the rays, right? So if the rays are distorted, what you see is distorted. Clear? If the rays are distorted, definitely what you see will be distorted. Clear? So as a result, your eye will try to recreate the image using these rays. So as a result, your eye will see the image here, right? Clear? Your eye will think that these rays are coming from this point. Clear? Your eye don't know the story that this is bending from this point. Okay? Eye doesn't know that story. Clear? So as a result, this is the real depth. Okay? This is the real depth. This is the real depth. This will be the apparent depth. Clear? This is the real depth. Clear? And this will be the apparent depth. Clear? So the object is actually here, but you see it here. Clear? But you see it here. Clear? So how can we create an equation for this real depth and apparent depth? Let's assume that this medium is n1 and this medium is n2. Let's assume that this medium is n1 and this medium is n2. Clear? Then I'll write this angle as I. Then this will be I. This will be I. Clear? Then I'll call this R. If this is R, definitely this will be R, right? Clear? If this is R, this will be R. Clear? So I can apply Snell law to this point. Clear? I can apply Snell law to this point. Clear? So then I'm gonna get, when I apply Snell law to this point, I'm gonna get n1 sine I, n1 sine I equals n2 sine R, equals n2 sine R. So I'll get sine I over sine R Sin I over sin R equals n2 over n1. Clear? Clear? And I have a small chance like this, okay? I need to convert them into tan angles. Then it provides me an opportunity to create an equation between capital H and simple h. That means, you know that for small angles, theta radian equals sin theta equals tan theta, right? Clear? For small angles, theta radians equals sin theta equals tan theta, right? And these angles are actually very small. Why? Although I draw this diagram like this, we are talking about a beaker and your eye. Your eye is really small, right? Your eye is really small. Although I draw the eye like this, your eye is really small. So as a result, all the rays coming from this coin to your eye must be really small, right? See? Clear? Although I draw this as a huge diagram, although these angles are huge in my diagram, in the practical scenario, these angles must be really small, right? Why? Whatever the rays come into your eyes should reach your eye, and your eye is really small, right? Your eye is really small. Clear? So practically these are angles that are received by your eye are really small. Clear? They must be really small. Clear? So now what I can do here is since these angles are small, sin theta equals tan theta, right? So I can write sin I equals tan I, sin R equals tan R, sin R equals tan R. Clear? Sin I equals tan I, sin R equals tan R. Clear? Equals n2 over n1. Equals n2 over n1. Clear? Then what is tan I? What is tan I? I'll mark this as x. I'll mark this as x. Now tan I can take using this triangle, right? Clear? Tan I can write using this triangle, this one. Clear? It's x over capital H, right? Tan I is x over capital H. Is that clear? Tan I can write using this triangle. It's x over capital H. Clear? Then what is tan R? Tan R is x over simple H, right? Tan R is x over simple H. Clear? So tan R x over simple H. Clear? Equals n2 over n1. Clear? n2 over n1. Clear? So x cancels out. X cancels out. I get simple H over capital H equals n2 over n1. I'll just write it in the other way around. It would be much convenient. Capital H over simple H equals n1 over n2. Clear? Clear? So this is the equation for the real depth and the apparent depth. So a method to understand this properly, okay? A method to understand this properly is this capital H depth, this one, it's formed by the rays in this medium, right? Clear? This capital H depth belongs to the rays in this medium, right? Clear? So in front of capital H, I'm going to write N1, refractive index of this medium. Then this simple H, it actually belongs to these rays, right? Clear? Simple H is actually formed by these two rays, right? These two rays, clear? So actually simple H belongs to this medium, clear? So in front of simple H, I'm going to write refractive index of this medium, N2, clear? The reason I'm asking you to remember this way is like, it's not like in O level, sometimes the I is in air, sometimes the I is in water, and you are looking out. Then things may change, right? Things may change. Sometimes you are looking at an object in water from air. Sometimes you are looking at an object in air from water. Like that, there may be different questions. So understanding it like that would be much convenient, clear? But the most general question would be, okay, the most general question would be, usually the most general equation will be this scenario. Usually if you take 100 questions, at least in 70 questions, you will keep your eye in air, right? You will keep your eye in air, right? At least in 70 questions, usually the eye is in air, right? So usually N2 is 1. Usually N2 is 1. So when N2 is 1, I get N1 equals H over capital H. So in many questions, you would have to use this, okay? That is refractive index equals real depth over apparent depth, clear? That means refractive index equals real depth over capital H is real depth, right? Capital H is real depth. Simple H is the apparent depth, right? So N refractive index equals real depth over apparent depth, clear? Is that clear? That's how we analyze this thing, okay? So you have to write this, because I usually include everything in the note, but the problem is now people, I mean, I usually ask you to write a note always, right? I mean, I have everything. This is the only lesson that we are going to write a note. The reason is otherwise you will never write this, you will never draw a ray diagram, and you won't be able to do that in the A levels also, okay? Because usually the usual method is I usually include everything in the note and ask you to draw it at home, but it never happens, right? But not being able to draw ray diagrams in optics lesson is a disaster, okay? Because this is one of the simplest lesson, okay? This is one of the simplest lesson. You can draw some diagrams here and there and get lot of marks. That's the optics lesson. So if you are not able to draw these diagrams, prove these kind of things, you are missing a lot. So we have to write these things in your note. This is the only lesson that we are going to write a note. So put the title as real depth, apparent depth, and write this. But attention, what I need you to do is put the title as real depth, apparent depth, and write this. But what I need you to do is focus on this properly, understand this properly, and if possible, try to draw the diagram and do the proof without looking at this, okay? Then it will go into your memory properly. Then you'll be able to recreate it again and again easily, okay? So try to draw this diagram and prove this without looking at the board, okay? Once look at the diagram and understand everything properly, and try to do that along, because it's really necessary. In A-level questions, they ask you to draw several ray diagrams, but they don't allocate lot of time for that, okay? Because these kind of ray diagrams are taught in the syllabus when we are teaching theories, so you don't have to think anything, you just have to draw. So they don't allocate lot of times if they give a question like this, okay? Okay. So the next one, hope it's enough time for this. And you have to know this apparent displacement, term called apparent displacement also. What is the term apparent displacement means? Apparent displacement means this thing. See here, the object is here and image is here. As a result, there's a certain displacement, right? As a result, there's a certain displacement, right? This we call the apparent displacement, clear? This we call the apparent displacement. And how can we get the apparent displacement? How can we get the apparent displacement? Apparent displacement we can get using that one. I can write simple h equals cross multiplying this, simple h equals what? Simple h equals capital H n2 over n1, clear? Capital H n2 over n1. Then apparent displacement is, see, capital H minus simple h. Apparent displacement is capital H minus simple h, which gives me capital H minus capital H n2 over n1. So I get capital H 1 minus n2 over n1, clear? 1 minus n2 over n1, clear? This is apparent displacement, clear? This is the apparent displacement, clear? This way you can get the apparent displacement capital H 1 minus n2 over n1, clear? So write this down. So sometimes in certain questions they may ask the apparent displacement. In certain questions they may ask the real depth or the apparent depth, okay? We have to work with everything. Try exercise 3, question number 1. Try exercise 3, question number 1 quickly. Exercise 3, question number 1. And if not given, use standard values for refractive indices. That means water is 4 over 3, glass 3 over 2, air 1. Use these standard values for refractive indices if not given. Water refractive index 4 over 3, glass refractive index 3 over 2, air 1. Clear? It's n equals capital H over simple h. So here capital H 1 minus n2 over n1 is the apparent displacement. Try exercise 3 question number 1 using only these two concepts. Okay. Exercise 3 question number 1. Try exercise 3 question number 1. Then question number 6. Exercise 3 question number 1 and question number 6. Just directly use the equation real depth over apparent depth equals n1 over n2. I mean, these are the standard refractive indices. Usually glass is 3/2, water is 4/3, air is 1. Okay, so question 1, exercise 3, question 1. Exercise 3, question 1. A crow flies 6 meters above the water surface of reservoir and sees a fish swimming 8 meters below the water surface. What is the visual depth of the fish as seen by the crow? How high above the fish is the crow flying as seen by the fish? The absolute refractive index of water is 4/3. So the idea here is you have water here, and there's a crow 6 meters above, crow 6 meters above, and there's a fish 8 meters below. Okay, 8 meters below. So these are just two dots like this. Okay, and I asked you to draw like neat diagrams. Neat diagrams doesn't mean that the fish has to look like a fish. Okay, I've seen people giving a lot of effort for that. So accurate diagrams means the information should be clear. Okay, but the fish need, I mean, doesn't need to look like a fish. Okay, so so this is 8 meters and this is 6 meters, and the refractive index is, this is 4/3, which is water, this is 1. So let's use the equation directly. This is the real depth, and real depth over apparent depth. Real depth over apparent depth equals n1 over n2. Attention, n1 over n2. Real depth over apparent depth equals n1 over n2. So here the real depth is 8. Apparent depth, I don't know. I'll call it simple h. Real depth belongs to this medium, so 4/3. Apparent depth belongs to this medium, so 1. As a result, I get h equals 6. Clear? H equals 6. So the apparent depth would be 6. So the fish will be seen at a height of h, which is 6. Clear? Clear? Then again, let's apply the equation for this one. Now the I is here, the object is here. Clear? So again, real depth over apparent depth equals n1 over n2. So in this case, the real depth is 6. Real depth is 6. And the apparent depth, I'll call it h dash, equals real depth belongs to this medium, which is 1. Apparent depth belongs to this medium, which is 4 over 3, which gives me h dash equals 8. H dash equals 8. Clear? So the bird will be seen at a distance of h dash equals 8. See? So here the both the bird and fish have disadvantages, right? Why? When the bird come to catch the fish, bird will see the fish at a wrong place, right? When the bird reach to catch the fish, bird will see the fish at this point, but it's actually here. Then the problem with the fish is, when the fish is looking at the bird, he won't accurately judge how close the bird is, right? Why? The bird will be seen further away. Clear? Bird is actually at 6 meters, but the fish will see the bird at 8 meters. Clear? So the fish will not accurately judge how close the bird is. Clear? The bird is closer than it looks. Clear? Bird is closer than it looks. Clear? Is that clear? So I mean, real depth of apparent depth equals n. If you remember it like this, you are in trouble in these kind of scenarios. But that equation, if you remember it the way I asked you to remember, then it won't be a big issue, right? Then real depth of apparent depth equals real depth belongs to this medium, apparent depth belongs to that medium. In this case, real depth belongs to this medium, apparent depth belongs to this medium. Clear? Clear? If you remember it that way, it would be much convenient. Clear? So try question number 3. Sorry, not 3, 6. Read and try question number 6. if you are done with question 6, yeah, maybe try question 3 also. It's not related to real depth, apparent depth, but it's also a nice question. Try question 3 also. So in the question 6, what they are mentioning is, I'm just doing questions here and there. That means I'm not doing the easiest questions. I'm doing questions here and there so that you can understand that the questions looks like this and how to understand a question. Then with that knowledge, you can actually try all the questions. Okay, that's why I'm doing questions here and there, including the most difficult questions, so that you can understand how to analyze different questions. So if I try question 6, a section of a rod 40 centimeter long is immersed vertically in water. When viewed from above the rod from air, it appears that half of the rod is submerged. Correct length of the rod. Rod sunk. So it's like this. Okay. What they are mentioning here is the actual length of a rod is 60 centimeters. Actual length of a rod is 60 centimeters. Actual length of a rod is 60 centimeters. Sorry, it's not 60, it's 40, right? Yeah, it's 40 centimeters. Actual length of the rod 40. And they need us to find this length which is underwater. Capital H. Clear? Capital H. Clear? But as a result of diffraction, this length will be shorter, right? Why? This point will be seen at a point like this. Clear? It will be seen at a point like this. Why? Real depth, apparent depth. Clear? Although this is the real depth of this point. Clear? Although this is the real depth of this point, when looked from above, this point will be seen here, right? Clear? That's what we call real depth, apparent depth, right? Clear? Is that clear? Now what they are mentioning here is something like this. When you are looking at this rod, you are not seeing this, okay? This is the actual diagram. When you are looking at the rod, you see this. Clear? When you are looking at the rod, you see this. Clear? When you are looking at this, you see it appears that half of the rod is submerged. It appears that half of the rod is submerged. That means when you look at this system, you see it like this is half of this. Clear? It's seen as half of the rod is submerged. Clear? It's seen as half of the rod is submerged. Clear? Half of the rod is underwater. Clear? Half of the rod is underwater. I mean, it's not half of the rod is not actually underwater. Clear? But it's seen as half of the rod is underwater. Clear? Is that clear? So now it's quite straightforward. If this is 40 and this is h, this will be 40 minus h. That means this will be 40 minus h. This will be 40 minus h. Then what will be h? What will be simple h? For that I can use the rule, right? Real depth over apparent depth equals n1 over n2. So in this case, real depth is capital H, apparent depth is simple h. Real depth belongs to this medium, which is water. Refractive index of water is 4 over 3. Refractive index of air is 1. So I can directly use n equals capital H over simple h, right? Clear? I can directly use apparent displacement equals capital H, real depth over apparent depth equals refractive index. Clear? I can directly use this equation. Is that clear, everyone? Clear? Clear? So I get simple h equals 3 capital H over 4. Simple h equals 3 capital H over 4. Clear? Is that clear? So that means this is 3h over 4, and it appears that this is equal to this. That means it appears that 3h over 4 equals 40 minus h, which gives you 7h over 4 equals 40, which gives you h equals 160 over 7. Clear? 160 over 7. Clear? Is that clear? Write this down. Is that clear, everyone? They are talking about what it looks like, okay? What is not actually happening, what it looks like. Clear? So there's a small request to discuss this again. While others are trying question number 3, I'll explain this a bit again. So what is actually happening is the total length of the rod is 40 centimeters and capital H is underwater. Clear? But you don't see this capital H, you see the apparent depth always, right? You always see the apparent depth. So you don't see actually capital H, you are going to see simple H. So to find this simple H, you can apply real depth over apparent depth equation. Clear? Then you get simple H as 3h over 4. This is the apparent depth. So when you look at the system now, what you see is this. Clear? And this top part, it is not distorted, right? It's above water. So you would see as it is, right? So this you would see as 40 minus h. This you would see as 3h over 4. And they are telling that it seems like they are equal in length. Okay, it seems like they are equal in length. So these two are equal. 3h over 4 and 40 minus h are equal, and you calculate this and get capital H. Clear? Please mention whether you understand it now or not. Did you understand it? Okay. Okay. So before moving to question number 3, I'll teach one more theory point, because if you are not, well, let's complete question 3, because if you know question 3, you will be able to like handle some other questions too. So by next week, no, I'll teach this theory point 2 so that you'll be able to finish exercise 3 then. Okay? Because there's no point of giving a lot of time for you to try questions here. I'll teach this theory point also, then you can try all the questions in exercise 3 and I can discuss many questions from exercise 3 next week. Okay? So the plan for next week is you have to try to finish exercise 1, 2 and 3. Mainly exercise 3 will be difficult. Some questions will be difficult, but try to a certain level. Attention, try to a certain level. Then next week I'll discuss many questions from exercise 3. Okay, let's do it that way. Many questions from exercise 3 and exercise 2. So one more thing to add. Attention, one more thing to add. Think of this scenario. You have glass or water here and you have the object here. You have the object here. Clear? You have glass or water here and you have the object here. Now what will be the apparent displacement? What will be the apparent displacement of this object? What will be the apparent displacement of this object? If this height is h, if this height is h, what will be the apparent displacement of this object? Try to understand this. There will be a ray moving like this, right? There will be a ray moving like this. Clear? There will be a ray moving like this. Clear? It won't be distorted at any point. Clear? Then this ray, it will move like this, then this, then like this, right? Clear? It will move like this. Clear? Then it will move like this. Now my eyes receive these two rays, right? My eyes will receive these two rays. Clear? So my eyes will recreate the image, so it will be seen at this point, right? It will be seen at this point. Is that clear? My eyes will recreate this one, my eyes will backtrack this one and this one, and it will recreate the image here. Clear? So as a result, the object is here, the object is actually here, but the image will be formed here. Clear? Then this will be the apparent displacement. Clear? This will be the apparent displacement. Clear? Then how can I find this apparent displacement? You can think of a scenario like this. Attention. You can think of a scenario like this. Think that the object is not here. The object is here, just below water. Clear? Clear? Just at this point. Clear? Clear? Assume that the object is here. If the object is here, where can you see the image? If the object is here, where can you see the image? Let's draw some lines. This direct ray will move like this. This direct ray will move like this. Clear? This direct ray will move like this. Clear? And this ray will move like this. Clear? This ray will move like this, right? If the object is actually here, this ray will move like this and this ray will move like this, right? Clear? And the image will be formed and the image will be formed at this point. Image will be formed at this point. Clear? So, for an object which is situated here, the image will be formed here. For an object situated here, image will be formed here. Clear? And we actually know the apparent displacement of this guy, right? We already calculated that. This is a natural scenario, right? You have water and you have the object. This is the same scenario that we analyzed in the previous diagram, right? This is the same scenario that we analyzed in the previous diagram, right? In that diagram, we calculated D. What was D? If this is H, it is H 1 minus N1 over N2, right? N1 over N2, right? Clear? Clear? Is that clear? Oh, N2 over N1. Okay. N2 over N1. So it entirely depends on what is 1 and what is 2. Is that clear? Attention. Is that clear? So the best thing here is this is a parallelogram, right? Best thing here is this is a parallelogram. Is that clear? This is a parallelogram. See this one? This one, and this one. This is a parallelogram, right? This is a parallelogram. Is that clear? So if this is a parallelogram, if this is D, this is D. Clear? If this is D, this must be D, right? Clear? If this is a parallelogram, if this is D, this must be D. Clear? And this D we know. Clear? Then it's the same apparent displacement. Clear? So we can tell that we get the same apparent displacement when the object is placed somewhere else with a gap from the actual medium. The story is the final conclusion is you will see the same apparent displacement when you are looking from above. Okay, you will see the same apparent displacement when the object is here, 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 and this gap doesn't matter. Clear? This gap doesn't matter. Clear? If the size of the medium is same, the apparent displacement will be same. Clear? Clear? If the size of the medium is same, clear? If the size of this medium is same, anyways the apparent displacement will be same. Clear? Is that clear, everyone? So write this down. So I anyways have to let you write these things, otherwise I can include them in the note. It was initially included in the note, but I learned a lesson through that. You are never gonna draw this thing. So now everything was removed from the book. Now you have to draw these things, because this sometimes for some people this will be the first and last time that you are going to draw this. Okay, although we ask you to draw this several times at home, for many people this is the first and last time that you are going to draw this, right? For sure. So we should at least draw the first time. So you can put the topic as apparent displacement does not depend on the gap between the medium and the object. Apparent displacement does not depend on the gap between the medium and the object. Just a random paragraph, okay? Just write it in a way that you understand. Okay? Apparent displacement does not depend on the gap between the object and the medium. Clear? Apparent displacement does not depend on the gap between the object and the medium. And about waves and oscillations lesson today 6:30, 8:30, or else maybe 6:40, 8:30, I'll be discussing the remaining practicals of waves and oscillations lesson. We have 1 or 2 practicals remaining in waves and oscillations lesson. I'll discuss those practicals, and if we have time, some more questions too. And staying for that session is not mandatory, okay? If you were doing waves and oscillations, it's good to continue, okay? So stay for the waves and oscillation part 6:30, 8:30, but it's not mandatory. If you are here for the optics lesson, You don't have to think about 6:30, 8:30 session. But anyways, if you have transport issues or anything like that, you can leave after the class. I'll anyways provide the recording of 6:30, 8:30 session, okay? I'll anyways provide the recording of 6:30, 8:30 class, so you can watch the recording later, okay? So with this, you can actually try all the questions in exercise 3. With this, you can try all the questions in exercise 3 actually. Some questions may be a bit difficult, okay? So just go through the questions and try to come up with answers for at least for the possible ones. Other questions, just read and try to draw the diagram, and if you can't get the answer, leave it there. Anyways, we have to do like at least 7-8 questions from this apparent displacement kind of stuff next week, okay? So next week I'll start the discussion with exercise 3. I won't give a lot of time for you to try questions in exercise 3 because now you can at least read them at home. So I mean, exercise 1 and exercise 2, yes, it's possible to finish. Exercise 3, at least try the possible questions. At least try to draw the diagram to a certain level. Yeah. So anyone need any further explanations of this? So the conclusion is, whatever the gap between the medium and the object, the apparent displacement is same, okay? Whatever the gap between the medium and the object, you would still get the same apparent displacement. Okay, so I'll stop it here for today. And I'll start the next discussion, waves and oscillations discussion, that means the practical session, around 6:40, okay? So if you are staying for the practical session, you can stay. It's waves and oscillation practical session. Otherwise, yeah, you can leave. Thank you.